All right. So the next presentation is from Benoît Denis from CEA-Leti, and the title of the presentation is Architecture Vision, Radio Optimization, and Network Orchestration for Distributed ISAC. Benoît, then floor is yours.
Thank you, Chef. So you confirm you see my screen, right?
Yes, indeed.
Good. Okay, so indeed, so my name is Benoît Denis. I'm a research engineer and a project manager at CEA-Leti, and I'm going to make this presentation on behalf of the consortium of the 6G ISAC project, which has been focusing on distributed forms of ISAC. So since the project has just started this year, beginning of January, I will mostly give you an overview and flavor of the current research activities carried out in this context along three main directions. So the first one is the distributed architecture. The second one is the high resolution processing capabilities, and third one is the semantic framework. So maybe being the very last to present in a row this afternoon, I feel like privileged because the ground has been very well prepared by my colleagues and very nice talks. So there's no need to try to convince you anymore about the mutual benefits from truly integrating sensing and communication services. So while relying on common spectrum, common infrastructure, and enjoying wide area mobile coverage, it's really a win-win process that we expect. So the fact that sensing data can really assist communications and the other way around, the fact that by fine-tuning or optimizing, let's say, the transmitted radio signals, we can expect to improve further the sensing performance. But then the question is, why do we need to move from standard ISAC to distributed ISAC in this context? So we have identified obvious limitations of the standard ISAC configuration, let's say. So if you have if you take an example like the single transceiver as a scanning, let's say a sensing node, unique sensing node, of course, you will have a problem of scalability. You will not benefit from global coverage, not either from, let's say, a very large synthetic aperture. So the idea is really to go towards multi-node scenarios and also to perform target handover. Another point is that while moving from single target tracking problem to the multi-target tracking problem, usually the problem is overly simplified in the sense that, of course, we all know that the complexity doesn't grow linearly with just the number of targets. So we really need new methods to properly and efficiently detect and track so many targets. And by the way, which are passive. So that means that we also need scalable data association pressure and coupled with distributed processing. And while discussing about processing, it's also quite obvious that fully centralized processing schemes would generate huge bottlenecks with respect to both frontal and backhaul. So the idea is really to reach a more balanced between local processing loads, hierarchical loads, and centralized load, but also to define the right and proper split between, let's say, the different tasks and also in terms of information flow. Last but not least, there's also an issue with respect to the support of a huge variety of sensing devices. So you would find different reconfigurable intelligent surfaces with different architecture. You would find massive MIMO, XL MIMO, distributed MIMO, full duplex devices, so on and so forth. So it's really hard to integrate the information coming from all those devices in a coherent way. So the point is really to come up with an harmonized and unified framework to be able to accommodate all these devices. And specifically, this is the let's say the ambition of the 6G ISAC project, which try to overcome all these limitations by, let's say, trying to achieve a larger scale, higher accuracy, and multi-target tracking, but not only, also to perform semantic reasoning on top of this. And for this purpose, so the activity is structured around three main directions or axes. The first one is about distributed architecture. So it's intended to support intelligent operation, but also at large scale and in a seamless way. again, with the right balance between centralized, hierarchical, and fully centralized embodiments. The second aspect is regards the high resolution processing capabilities, so which obviously will benefit from distributed multi-view observation and signal acquisition, but not only, also benefiting from multiple bands and so on. And so for this purpose, we also need to finally optimize the physical layer, but not only, we also need to design specific supporting protocols and flexible resource allocation schemes. And the last point is about the semantic and goal-oriented framework, which largely inherits, or let's say rely on machine learning and artificial intelligence. It will impact, let's say, various components of the network, but also various layers of the, say, classical protocol stack. The point here is really to enable continuous learning and enrich, let's say, knowledge to be able to improve further the next sensing and/or communication task. A few words about the project on its own. So in a nutshell, it's again, it started in January this year. Will last for 3 years, so till the end of 2026, and it includes 10 partners, including partners from academia, a research center, 5 from industry, and 1 SME. After analyzing the use cases, say put forward in the standards, so namely the 3GPP release 19, we had the confirmation somehow that we would need this combination of unique features from the distributed ISAC embodiments. And especially in the context of very demanding wide area digital tuning. So that's the reason why also we identified in the project 2 main use cases, let's say priority use cases. One regards the intelligent transportation application. So typically to perform, let's say, the monitoring or let's say to enable also the efficiency of the traffic, but also the safety of vulnerable road users. So typically we are here in the presence of urban digital twinning, for instance. The other use case concerns smart factory, when of course you can imagine, let's say, coordinated fleets of robots or AGVs that need also to operate in an efficient and secure way in a very crowded environment, and so on and so forth. So now back to the main pillars of the research activities in the project. So the first one is a semantic framework. So what does it mean exactly? So basically, it's just it consists in applying concepts from semantic communications and to apply it to the different the various components of and layers of the distributed ISAC system. So this comes along with the fact that we need to move from, let's say, traditional data fusion paradigm to let's say a more semantic oriented composition paradigm. By semantic composition, I mean the understanding of, let's say, some context by composing the meaning of unitary or individual sensing events or even features. For this purpose, we also need a semantic channel, which is a logical channel to, let's say, provide instruction, especially with respect to the radio access network, typically. And finally, we need also to adopt a train while communicating and sensing approach. Again, the idea is really to enrich the knowledge in such a way that we can improve further the performance of the system in terms of both communication and sensing for next time. But if I can just take maybe a more concrete example. So if we are in the phase of acquiring sensing data, so typically the semantic plane could issue some knowledge-based upper layer semantic instruction that in the end would impact the run decisions and settings. So typically we need to define the kind of sensing signals that need to be sent in terms of bandwidth, rate, power, so on and so forth, even the waveform. We also need to define the kind of signal processing that needs to be implemented on the receiver side, and also the kind of radio metrics that needs to be extracted. Once the sensing acquisition is done, we need also to communicate the sensing data to the fusion center. So and likewise, so the semantic plane could issue some semantic instruction that would influence the run decisions and settings. So typically we need, so if we are more like on the source side, we need to define the type, the representation and compression of the data, the sensing data that will be encapsulated in the message transmitted to the fusion center. But we also need to define the, let's say, the acceptable or affordable link quality in such a way that we're still able to infer the semantic symbol, for instance, in this sensing context, while deliberately degrading the performance in terms of transmission. So typically by degrading the transmit power, choosing let's say the adequate MCS, or even coming up with more compact waveforms typically. So this is exactly where the emphasis is put for now in the project. So we have activities in terms of semantic-based waveform design at the link level, and the idea is really to, for instance, perform data compression of the sensing data. But the other way around, also the semantic plane out of intermediary fusion result, but also possibly low-level RAM matrix could kind of extract information, compose meaning for further reasoning, and again with the final goal of enriching the knowledge for the purpose of improving further the performance of the overall system for the next sensing or communication events. And this interplay, which is quite complex between the semantic domain and the radio domain, raises a couple of questions, especially with respect to the architecture. So these questions are typically the kind of interfaces, where to control the semantic plane, so on and so forth. So those questions are currently investigated in the context of the project too. So speaking about architecture, again, as a reminder, we need the support to distributed processing, support for seamless integration of a wide variety of sensing nodes. We also need to perform multi-target tracking at large scale and to support the semantic layer. So if I come to this more concrete example, so this is a preliminary draft and attempts put forward by our colleagues and partners from Nokia, which is largely inspired by the ORAN architecture. So you see here, so it's the example is even in a multi-static case. So you would see here this SEPF, so standing for the sensing processing function, which is hosted in the core network, which can admit directly input data from the end user itself. So typically channel measurement reports on positioning reference signals, or even SRPs, so on and so forth. But it can also complementarily accept some input data directly from the DU. So typically accounting for G-Node-B measurement reports, or even pre-processed data. So typically, if I am to give also an example of the kind of low-level processing that can be hosted at the DU, here you see, for instance, some kind of peak detection algorithm. So let's say retrieving the quadruplets of angle of arrival, single strength, Doppler polarization out of the spatial channel impulse response, and this more, let's say, more compact data representation can fit the SEPF for higher level processing, which can be also possibly distributed. So as possible examples, we have of course fusion, but it could be also scene reconstruction, integrated check, like you check the integrity of location or velocity data. It can be also object classification and so on. Besides the SEPF, we also need the SEMF, which somehow occupies approximately the same role as that of the LMF for those who are familiar with the 5G positioning. So typically this block is in charge of managing both the distributed sensing and acquisition and processing, but also the sensing data itself. Of course, this is still, it's at the draft level and still quite premature. So these are also actions that are currently ongoing in the context of the project. Now, moving on to the second pillar, so the high resolution processing, but still in the context of distributed settings. So here, I just show you a simple scenario where you have multiple sensing nodes in a monostatic way, let's say, which are distributed. And so the point is really to benefit from the spatial distribution of those sensing nodes, but also from the possibility to distribute the calculation. So typically here, this joint detection and localization problem of the multiple targets is stated in terms of a composite multi-hypothesis testing problem. And our colleagues from the Chalmers University came up with this generalized information criterion-based detector that can jointly extract the targets themselves and estimate the parameters. And the very good point is that they also proposed, let's say, some kind of low complexity decomposition of this initial problem into lower dimensional optimization problem in such a way that there's only need to compute very, let's say, lightweight log likelihood ratios at each of the local station, and this is then forwarded to the fusion center that is in charge of performing one-by-one target detection through iterative constellation. So this is exactly here an illustration of the process. So you see at the bottom figures, so we are in the 2D position plane. And the bottom one are the velocity plane. So and column-wise, it's just the step-by-step process. So you see that at each iteration, we are able to clearly identify the current targets and to estimate the parameters. And in such a way also that this target can be removed for the next steps. And now, if we are mostly interested in let's say, macroscopic level of the performance assessment. So we see that the performance with this kind of approach is in terms of probability of detection and MSE of the positioning approaches that of the, let's say, an idealized case where we would just need to treat a single target case. As another example of high resolution processing in the distributed context. So here we are in the presence of a user equipment transmitting in uplink with respect to a network of distributed radio stripes. And those radio stripes, they form some kind of, let's say, a large sparse array. And the good point is that if we consider phase synchronized radio stripes, we are in the context of coherent processing in such a way that so this network of radio stripes form this very large array, and the point is that the UE lies in the near field of this synthetic array in such a way that we can really fully benefit from the near field effect in such a way that we can also achieve high resolution estimation. So the point here is really to jointly estimate both the locations of scattering points, or originating from scattering objects around, plus the location, the clock offset, and the phase offset of the UE. And the phase offset, in the context of phase synchronized schemes, there's only one phase offset with respect to the UE to be determined. So again, our colleagues came up with this nice maximum likelihood solution, and also low complexity variants. And in a nutshell, so if we are interested in non-coherent processing, so here is a heat map of positioning error bound. So the theoretical analysis show that typically the positioning of the UE in case of, let's say, narrower bandwidth, and so the position error bound is dominated by the angular information. As you can see here, you see, for instance, the effect of the superposition of the, let's say, the reflected path from both the specular reflection on the walls plus that of the scattering points, which superpose or overlaps with the direct path in line of sight. So it means that we degrade the estimation performance. And as we go for a larger and larger bandwidth, so typically here, we see that we have, let's say, more capability to resolve those multipath components in such a way that we enjoy better estimation. And in this case, the analysis of the error bound show that the bound itself is dominated, sorry, by the delay information rather than the angular, like in the previous case. Now, if I'm interested in the comparison of the positioning performance for UE versus scattering points, we see that the UE positioning through coherent processing is really accurate. So typically on the order of a centimeter or so, despite the fact that we operate in sub-6 giga bands here. But at the same time, it's also quite sensitive with respect to low SNR. This results from the fact that the cost function to optimize in this case is very picky. So that's also the reason why we are more sensitive with respect to SNR. Whereas in the case of scattering point location estimation, of course, we are far less accurate, but as we do not rely on carrier phase information to locate, it's somehow still fairly robust in the sense that the cost function to optimize is smooth, and then we as we can see here, you don't suffer from outlier in the ECDF of the location error. But in the project, so besides those, let's say, theoretical-oriented work, we can also leverage the some real-life proof of concept platform and demonstrators. So here is another example. So this is developed by Nokia again. So we have a sensing system operating in FR2 band and relying on standard OFDM waveform. So here we are in the presence of a quasi-monostatic radar system, in the sense that we have a G0B RU in TX, which eliminates the scene, and we have by its side we have a sniffer RU, which is just in charge of beam scanning the environment, looking for reflected signals from targets. Both are synchronized through cables. We operate in TDD, and we perform some kind of OFDM radar-like processing that includes obviously clutter removal. And this part of the processing can be hosted at the DU, for instance. Let's say the basic operations, as long as they are fed by input measurements coming from the RU, can be hosted at the DU. Whereas, let's say, higher level processing, like Kalman tracking, for instance, can be perfectly processed at the SCPF. So this is just to make a small reminder with respect to the architecture that I just presented beforehand. And you will retrieve this system here, mounted on a mast or a pole here on the right of the video. So this has been intended for high precision short range indoor sensing in a line of sight environment, so in a production hall. You see here two pedestrians walking in opposite directions. And on the right, you see here on this range versus real relative speed diagram that we can identify those two masses accounting for the two pedestrians. So this is still in a monostatic mode. So this means that obviously in the context of this CG ISAC, which again put emphasis on distributed settings, we need to foresee extension into distributed configuration. So one, let's say, first straightforward way to move forward is to consider multiple monostatic sensing nodes. So typically benefiting from multiple viewpoints. And enabling data fusion, both data fusion and target handover. But another alternative would be also to go for multi-static acquisition, for instance, typically while relying on GNSS synchronization signal or G0B as supported by the 5G standard, for instance. But this, it's a demonstration is one among others. So we have also other demos in the context of CG ISAC. So here at the center, you recognize the previous platform, but we also have, let's say, initiatives that more the link level. So typically here, the semantic-oriented waveform design. So really link level communication, again, for the purpose of showing data compression of sensing data, for instance. We also have, let's say, demos which enable offline validation based on channel sounder and equipment, like also devices like RIS in different operating modes. So it could be reflective or hybrid RIS, and also tested in anechoic chambers. And finally, we also have some radio SLAM foreseen in the context of, let's say, multimodal detection at a urban intersection. So it's more like a system level vision, let's say, and including also other modalities, non-radio modalities like video and so on. That being said, so the couple of results that I presented you today, they are, of course, it's not the end of the story. We also have many other key challenges that are addressed in the CG ISAC. For instance, we have actions and developments regarding the modeling of multistatic backscattering, including near-field effect. We also have the upgrade of deterministic simulation tools for both performance assessment and also to feed the machine learning tools. We have developments regarding waveform design, as I already mentioned, but also more generally speaking about physical layer optimization, spectrum management, and also sensing-aided communications. And finally, we also have actually regarding sensing data representation, protocol design, resource allocation, and orchestration. And the idea is really to define the best operating trade-off between communication and sensing services. And that being said, this will conclude my speech today. If you are interested in collaborating with us, I invite you to contact either Emilio Calvanese, the main project coordinator, or Henk Wimmers, who was co-chairing the session this morning with the technical manager. I also invite you to have a look at the two first consortium papers, so one issued in the context of EU CNC this year, and another one which is still upcoming and to appear in IEEE magazine. And that's it from my side. I thank you for your attention.
Perfect. Thank you very much, Benoît. And this is a really great presentation and the whole overview over distributed ISAC and semantic sensing and communication. For the since we are a little bit late on time, I think we will go now on a break. I think you have one question in the chat, so please,
okay.
It would be great to address that.
Okay, I will. Sure.
Thank you so much, Benoît.
Yep.